Welcome to ATMOS 5000 day number 24. We're still working in Stull chapter 14 and we're focusing in on sections 14.6 and 14.7. We'll be looking at convective inhibition, the triggers of convection, talking specifically about the different lifting mechanisms that exist. And then we'll work on thunderstorm forecasting and we'll introduce stability indices and how they can be used for thunderstorm forecasting. So we've seen this before. We have our air parcel, which is being lifted dry adiabatically until it reaches the lifting condensation level. And above the lifting condensation level, it follows the moist adiabat, which is the blue line in this case. And then we have the integrated area between the level of free convection and the equilibrium level, which is defined as the convective available potential energy. And then we have the area below, between the lifting condensation level and the level of free convection. That integrated area is the convective inhibition. The units on both of those are joules per kilogram. And the convective inhibition mathematically is the integration from essentially ground level up to the lifting level of free convection. It's gravity times the buoyancy, essentially the virtual temperature of the parcel minus the virtual temperature of the environment divided by the virtual temperature of the environment times the increment of height over which that buoyancy is acting. So that's your delta Z. So it's essentially the analog of the CAPE, except for now we're looking at the parcel is going to be essentially colder than the environment. So the convective inhibition, like CAPE, has an interpretation. So when you have no convective inhibition, a SIN value that's greater than 0, there's no cap, and that is going to allow weak convection. And the more negative that the SIN becomes, the stronger the cap. That's great for limiting convection up to a point. The moderate values of the SIN between -20 and -60 is a moderate cap, and those are the best conditions for the cumulonimbus clouds. If you have a convective inhibition of -60 to 100, that's a really strong cap. It's difficult to break, and if it does break, it means that you've got a really strong lifting mechanism to overcome that. And if you have SIN value less than -100, that's an intense cap, and it's probably going to limit your convection that day, unless you have absolutely forced lifting. So let's talk about these triggers, these lifting mechanisms. During in-class exercise, we actually identified several of these. We identified surface heating and cooling above the surface. We identified surface convergence and divergence aloft. And we also identified frontal lifting and flow over terrain, so orographic lifting. Some other ones that are more advanced concepts that we're really not going to talk about in this particular class. One of those is positive vorticity advection. Vorticity is the rotation in the atmosphere, and there's a certain type of vorticity that when it moves can lead to upward motion. Humidification of the atmosphere. Recall that a air parcel of the same temperature, a dry one versus a moist one, have different buoyancies because they have different densities. And then absorption of solar radiation in the atmosphere can also lift air parcels. If you happen to have a layer of something that is absorbed, that absorbs solar radiation, it can heat that layer, which can cause local instability and convection at those locations. So let's look at these individually. So here we have surface heating. So we have an air parcel. We launched a Raywinson balloon. The surface temperature was 10 degrees Celsius, and the temperature at 2 kilometers above the surface was 0 degrees Celsius. And for reference, we have the dashed black line, which is the dry adiabatic lapse rate, which is the -9.8 degrees Celsius per kilometer. And in this case, when we lifted that air parcel to 2 kilometers, the atmosphere, so if we lifted by the dry adiabatic lapse rate, by the time we get to 2 kilometers, our air parcel is colder than the environment, which means that it's going to be negatively buoyant. And if you let go, that air parcel will return to the surface and will be therefore classified as a stable atmosphere. But if we start to heat the surface, we will affect the atmospheric lapse rate. So here we have heated up the surface, and then that heat has been mixed in the lowest 2 kilometers of the atmosphere. And so it's changed the environmental lapse rate. The lapse rate is not quite as steep as it was, it's actually decreasing faster than it was before, which means that it's actually slightly more, less stable than it was before. And as we continue to heat the lower part of the atmosphere, we will make the atmosphere progressively more unstable. So by the time we heat the surface up to 20 degrees C, we now have a lapse rate that is essentially parallel to, or in this case, equivalent to the dry adiabatic lapse rate. And that's going to be defined as a neutral atmosphere. And if we continue heating the surface, we will now cause the atmosphere to be unstable because the environmental lapse rate is decreasing at a faster rate than the dry adiabatic lapse rate. And the atmosphere will spontaneously convect at this point because you actually have a fluid of a lower density underneath a high density fluid, and it will automatically overturn when it becomes absolutely unstable. And the only change here was the heating of the lower part of the atmosphere through the absorption of solar radiation at the ground. We can achieve a very similar process by, instead of changing the temperature at the ground, by instead cooling the atmosphere aloft. So here we launch our Raymond-Sun balloon. We had a surface temperature of 25 degrees C, and the temperature at 2 kilometers was 15 degrees Celsius. And that would correspond to essentially a stable atmospheric situation. But let's say that we have some cold air advection above the surface, and so you have cooling of the atmosphere aloft. So here we have a situation where the temperature is decreased by 5 degrees at 2 kilometers. It's become less stable than it was before. As we continue to cool, we now have an environmental lapse rate that is equivalent to the dry adiabatic lapse rate. So that would be a neutral atmosphere. And if we continue cooling aloft, we will make the atmosphere unstable by having a very large atmospheric lapse rate to where you now have a lower density fluid underneath a higher density fluid, and you'll have spontaneous convection or overturning of the atmosphere because it's absolutely unstable. Another way that we can lead to vertical motion is surface convergence. So here we have a column of air with an air parcel. The air parcel is denoted by the blue box. And we're going to have surface convergence, and then we'll watch what happens. So imagine that you had a balloon in your hands and you squeezed that balloon while that balloon was sitting on a table. The air cannot go through the ground, and in response to the pressure or the forcing that you have on the sides of the balloon, the air will squirt out the top, leading to essentially rising motion. And the surface convergence will lead to upward motion. And if you have enough upward motion, that can actually lead to cloud formation if you lift the air parcel up to the lifting condensation level. It doesn't have to be that way, but if you do lift it up to the LCL, a cloud will form. So here we have a column, and we're going to have divergence aloft. So that means we're going to have air that's moving away from each other at some elevation above the surface. So let's animate that. So here, we essentially took air from the middle of this air column and removed it from the air column, which generated essentially kind of a low pressure anomaly. And the air will respond to that low pressure anomaly by moving to fill that void. So in this case, it'll lead to upward motion below the divergence and downward motion above the divergence. And once again, if you happen to lift the air parcel high enough to where it reaches the lifting condensation level, that can actually lead to cloud formation. It doesn't have to be, but it could. So we also talked about fronts being sources of lift. So the basics of weather fronts are that fronts are different air masses. So here we happen to have a cold air mass on the left with a dry air mass on the right, and the boundary between these air masses is shown by the blue line with the triangles on it. And that cold air is moving from left to right. And because the air is colder, it's more dense than the warm air. And so that cold air, as it moves, will dive underneath the warm air, which can lead to vertical motion of the air parcels that are being lifted out of the way. Let's animate that. So that cold wedge is moving underneath the air and driving it up. We can also have a warm front. In the case of a warm front, we have a cold air mass, and we have warm air that is being advected towards the cold air mass. But because the warm air is less dense than the cold air, it will ride up underneath the cold air. This will be a rather gentle slope compared to the cold front, where you had the cold air that was diving underneath the warm air. And let's animate and see what happens when we lift that air parcel. As that warm air is moving, it's got to rise. We could also have a dry line, but we're not going to talk about that right now. And here we'll focus in on flow over topography. So here we happen to have an isolated mountain, and air that's flowing towards this mountain, given the opportunity, will flow around it. But if you happen to have a long ridge, then there's no choice but for the transverse flow to increase in elevation and move over the obstacle. In that case, you have forced ascent over the topography, which we refer to as orographic lifting. And you'll notice that the air parcel descends on the backside of the ridge as well. And if you happen to have a moist air parcel, or you manage to lift it high enough, you can achieve the lifting condensation level and form a cloud. But that cloud that forms will dissipate on the backside of the ridge as the air begins to descend. Because as the air descends, the temperature will increase, which causes the saturation vapor pressure to increase, which causes the relative humidity to decrease. And as soon as the relative humidity drops below 100%, then the cloud will dissipate. So a lot of times when this situation occurs, what you'll have is a standing wave cloud. This cloud will remain fixed relative to the topography underneath, even though the air parcels are moving through the cloud, constantly in motion, rising up above the peak and then descending on the other side. The air parcels are passing through the cloud, but the visible cloud structure remains anchored to the topography underneath. So next, we'll move on to thunderstorm forecasting. So there are three types of thunderstorm, essentially, descriptions that are put out by the National Weather Service. The first are outlooks, and these outlooks are just a general forecast guidance for broad regions. They tend to be long-range forecasts, 6 to 72 hours, saying, in this three-state area, the likelihood is that conditions are going to be conducive for thunderstorms in the afternoon of such and such a day. It's kind of a broad, this is what's, we're going to take a closer look at it moving forward, but that's what we think's coming down the pipe. And that's as opposed to a thunderstorm watch. Thunderstorm watches are shorter forecasts, up to 6 hours, basically stating that severe weather is favorable within specific regions. Now remember that severe weather does not refer to just run-of-the-mill thunderstorms. It refers to thunderstorms that have damaging winds, winds in excess of 25 meters per second, or hail that is essentially greater than 3/4 of an inch in diameter, or tornadoes. And so these watches are basically, let's within these specific regions, say, often denoted by boxes on the maps, then these are the areas that we're watching for severe weather because it's favorable. And that's as opposed to warnings. Warnings are basically nowcasts, which basically means this is what's going to happen in the next hour. And when you see a warning, it means that the severe weather is already occurring and it's headed your way if you happen to be in the zone where the warning is happening. So this could be a severe thunderstorm warning. This could be a flash flood warning. This could be a tornado warning. All of those things are possible. Just like you can have tornado watches, you can have severe thunderstorm watches, you can have flash flood watches along the way. So that severe weather definition that I alluded to is tornadoes, damaging straight line winds greater than 25 meters per second or 56 miles an hour, hail with a diameter greater than 3/4 of an inch, or flash flooding. And interestingly enough, all thunderstorms contain lightning by definition. Thus, lightning is not included in the list of severe weather, even though lightning happens to kill more people each year than tornadoes, winds, or hail. So you just have to assume that all thunderstorms are dangerous when it comes to lightning, and you should take precautions. And we'll go over those precautions when we start talking about thunderstorm hazards in Chapter 15. So stability indices are used for thunderstorm prediction. We've already actually kind of introduced some of these without actually calling them stability indices or thunderstorm prediction tools, but we've introduced the concept of the level of the lifting condensation level, the level of free convection, the convective available potential energy, and the convective inhibition. So all of those are things that we can use for thunderstorm prediction. So for example, if we have a sounding and it doesn't matter how high you lift the air parcel, it doesn't form a cloud, so there is no lifting condensation level or there is no level of free convection, then no thunderstorm is going to happen that day. Similarly, if the convective available potential energy is 0, then there's not going to be a thunderstorm because there's no energy available for a thunderstorm. Or if the convective inhibition is greater than 100, or I should say less than -100, then their cap is so strong that it's almost impossible to lift an air parcel up to the level of free convection. So all the LCL, the LFC, the CAPE, and the SIN are not great predictors of thunderstorms, but they can tell you that a thunderstorm is not going to happen if they happen to be certain values. The new indices that we're going to introduce are the K index, the lifted index, the Showalter Stability Index, the severe weather threat index, and the total totals index. The basic idea of the stability indices is that you come up with a single number that characterizes the stability or instability of the atmosphere. They are easily computed, they're easy to apply, but the disadvantage is that there's no single stability indices that can be used to identify or predict thunderstorms, that there's lots of different stability indices, and you kind of have to look at a lot of them in order to understand the overall picture of what's going on. So let's take a look at the K index. The K index basically is trying to measure the thunderstorm potential, and it's looking at the lapse rate of the atmosphere between 850 and 500 hectopascals, or between 85 and 50 kilopascals. So it's looking to see if that atmospheric layer is stable, unstable, or neutral. It's looking at the moisture content of the lower atmosphere. So that's the dew point at 85 kilopascals. If you have no moisture, then that's going to be a problem for thunderstorms because you need lift, instability, and moisture. So the first term there is looking at the instability. The second term is looking at moisture. And the third term is looking at how deep that moisture layer actually is. Does that layer extend from 85 kilopascals up to 70 kilopascals? And so you have these three different terms. You have the instability term. This is the temperature at 85 minus the temperature at 50 kilopascals. You have the low-level moisture, the dew point temperature at 85. And then you have the mid-level moisture, or essentially trying to figure out how deep that moisture extends in the third term. And so the temperatures here in calculating the K index are all done in degrees Celsius. And the interpretation of this is if the K index is less than 15, then there's a 0% chance of thunderstorms. And by the time you get up to a K index between 26 and 30, there's a 40 to 60% chance of thunderstorms. And by the time you get up to a K value of 40, you have a 90% chance of thunderstorms. So keep in mind that the way that the K index was crafted, it does not account for all three requirements for a thunderstorm to form. Remember, you have to have lift, instability, and moisture. The K index is only looking at the instability and moisture. You can have a high K index, but if you don't have a lifting mechanism, it's not going to realize a thunderstorm. So that's why the percent of thunderstorms never gets to be 100 with the K index, because you still have to have a lifting mechanism. This particular K index works best for non-severe thunderstorms, in part because it doesn't have any information about wind shear. It's only looking at instability and moisture. Next, we have the lifted index. And the lifted index is perhaps the simplest of all of these. And what it's doing is it looks at the comparison of the temperature of the environment at 50 kilopascals minus the temperature of an air parcel that is lifted from the boundary layer up to the 50 kilopascal layer. And if the environment is warmer than your air parcel, then the lifted index is positive. And basically that means that that air parcel is negatively buoyant because the environment is warmer than the air parcel, so the air parcel is colder, so the air parcel is going to sink. If you have an air parcel that is positively buoyant, it's warmer than the environment, you'll have a negative lifted index. So there are lots of different ways to determine the mean conditions of the boundary layer. A lot of people just use the surface values, but the surface values won't give you the most accurate value for the lifted index. So here we have the procedure for calculating the lifted index. So we start off with determining where the boundary layer is at. In this case, we identify the lowest 10 kilopascals of the sounding. And we find the mean mixing ratio, R. When in this case, it's listed here, this one as W, but it's often, we're using it as R. And the mean potential temperature in the lowest layer. And then once we've identified those mean conditions, then we essentially lift that air parcel to determine the lifting condensation level. And then from there, we'll take the moist adiabat up to the 50 kilopascal layer and compare it to the environmental temperature at that level. So for this particular example, we have a temperature of the environment is minus 32 degrees C at 50 kilopascals. The temperature of the air parcel is minus 26. So minus 32 minus a minus 26 gives you a lifted index of minus 6, which means that that air parcel is positively buoyant, and there's essentially a 6-degree temperature difference at that layer, which is quite a significant buoyancy. So how do you determine the mean value of the boundary layer, that lowest 10 kilopascals? So you basically have to identify the maximum and minimum potential temperature within that layer, and the mean potential temperature is located 5 kilopascals above the surface and halfway between the maximum and the minimum potential temperature. And you do the same thing with the mixing ratio, R. You find the maximum and the minimum in that layer, and you'll take the average of those. And that gives you your starting point for calculating the lifting index. So the guidelines for this is if the lifted index is positive, then thunderstorms are not going to happen because the air parcel is negatively buoyant at 50 kilopascals. If you have a lifted index between 0 and -2, thunderstorms are possible, but they're going to need forced descent. If the lifted index is between -2 and -5, then the atmosphere is considered to be unstable and thunderstorms are probable. And if it's less than -5, it's a very unstable atmosphere and strong thunderstorms are probable. So there are problems associated with the lifted index in that it doesn't have any information about wind shear, and it's particularly good at forecasting surface-based convection. And although it doesn't explicitly include moisture, it implicitly includes moisture by looking at the temperature of the parcel that is lifted above the level of free convection. And that extra heating that you get from that air parcel is what drives the lifted index, and that heating comes from the condensation process. So oftentimes when I see a lifted index of -6 or -7, I think, oh my gosh, this is a potentially severe thunderstorm day with potential very strong tornadoes. The Showalter Stability Index is looking at the temperature difference between the air at 50 kilopascals and the temperature of an air parcel that is lifted from 85 kilopascals. Instead of taking the lifting an air parcel from the boundary layer itself. So it's very similar to the lifted index, but the starting place, the starting air parcel, is defined differently for the Showalter Stability Index. But otherwise, it's very similar. So in this case, we just grab the air parcel at 85 kilopascals, lift it to the lifting condensation level, and then take it up the moist adiabat, and then compare the temperature of the air parcel at 50 kilopascals to the temperature of the environment at 50 kilopascals. And here, if we are looking at this, we have forecast guidelines very similar to the lifted index. If you have a Showalter index less than -6, it's extremely unstable and strong thunderstorms are probable and tornadoes are possible. And it's kind of best for forecasting that mid-level convection, starting at 85 kilopascals. But it really ignores the moisture in the boundary layer. And if you think about thunderstorm formation, you need lift instability and moisture. Then, if there's significant moisture, below that level of 85 kilopascals, then we won't know about it. Similarly, if it's dry down there, this method won't know anything about that either. And that's why a lot of people use the lifted index as opposed to the Showalter index. Next, we have the SWET index, the Severe Weather Threat Index. And it includes information about the low-level moisture, the instability using the total totals that we'll talk about here shortly. It includes information about the wind the low-level winds at 85 kilopascals and mid-level winds at 50 kilopascals. And it also looks at warm air advection. So it's looking at dew point temperatures, warm air advection. It's looking at the wind direction at 50 kilopascals and 85 kilopascals as well. So it's got a lot of information about wind shear. And because it also includes information about wind shear, none of the other stability indices that we have looked at yet include information about wind shear. So this is going to be primarily used to diagnose the presence of severe or the forecast severe weather. Because recall that severe weather requires lift, instability, moisture, boundary, and shear. And this is the first of the stability indices that includes information about shear. So the wind speed at 85 kilopascals and 50 kilopascals is included in units of knots, and the wind direction is in degrees. So there are a couple of rules associated with calculating the sweat, and one of those is that none of these terms can be negative. So if the dew point temperature, which is in degrees Celsius, is negative, then you'll set that first term equal to 0. If the total totals, which we'll talk about how to get here in a second, are less than 49, then the second term essentially would be less than 0, and we would define that term as 0. And then, if the vertical wind speed is such that anything turns up to be, if any of the following conditions are not met, then we basically set these terms equal, the last term equal to 0 as well. So if the wind direction at 85 kilopascals is not in the range between 130 and 250 degrees, and the 50 kilopascal winds are not in the range between 210 and 310, or the direction is greater than 0, the change in direction is greater than 0, or if the wind speeds are both greater than 15 knots. So we're kind of looking for all of those sorts of things. If any of those are not met, not just one of them, but if any of them are not met, then that final term will go to 0. So for the forecasting guidelines, if we're trying to use this to forecast severe thunderstorms and tornadic thunderstorms, then we're looking for sweat values greater than 300 or sweat values that are greater than 400. This really only indicates the potential for severe weather. It really doesn't talk about thunderstorms in general. And oftentimes we need forced descent to realize that potential, because we'll often have convective inhibition that we have to overcome. And total totals index is included in the sweat totals, or in the sweat indices, and we have to define what the total totals are. And it's used to identify potential thunderstorm development, and it focuses in on the atmospheric lapse rate between 85 and 50 kilopascals, and also includes information about the low-level moisture at the 85 kilopascal layer. So once again, we're doing these temperatures in degrees Celsius. So it's combining the temperature at 85 kilopascals plus the dew point and subtracting off the temperature, 2 times the temperature of the environment at 50 kilopascals. So the forecast guidelines are total totals less than 45, no thunderstorms. And by the time you get to total totals greater than 55, you have strong potential for thunderstorm activity. It's good for air mass thunderstorms, and it's more reliable than the K index for severe thunderstorm potential. And it's because of that, it is actually used within the sweat index to help predict the formation of the thunderstorms, and then the sweat index includes additional information about the wind shear to determine the probability of severe weather. So Stull has this summary of all of these stability indices in table 14-6, which is reproduced here. And so now we've talked about all of these, the K index, the lifted index, the Showalter index, the severe weather index, and the total totals index. And here we're bringing it back full circle. This happens to be the Norman, Oklahoma sounding from May 20th of 2013. And I wanted to highlight the calculated stability indices that are shown on the right. So in the dark green, we have the K index of 24. We have a lifted index of minus 8.56, a Showalter index of minus 2.56, a sweat index of 363.7, and a total totals of 55.40. And I encourage you to use these values from the sounding and go back and compare it for the interpretation of these different stability indices for this particular sounding, and see if you think that this sounding is likely to produce severe weather later on in the day. And just so you'll know, this was hand-picked because it did produce an F5, EF5 tornado later in the day. And you'll see that all of these stability indices are essentially pointing in that direction.